Hi, my name is Andrew McLaren. We're going to talk about representing solutions using particle models, which is part of 3.8, but it's also related to 7.8. So we'll talk a little bit about that and how that relates. We're going to try and do some conversations around the standards and the main ideas here, and then we're going to look at some typical problems that kind of look like this, where they will have some sort of excess. Like you can see this guy is in excess compared to the other reactant, and you're trying to figure out what ions are now present. So there's some sort of precipitation, there's a solution that's being drawn, there's some ions, and there should be something that you need to add into that model. So you should be able to figure out the relative number of particles that should be drawn in here. And they also want you to model interactions sometimes, but it's not always the case. But it's good to be able to know how to do that because that does show up on like the multiple choice part if it's not on the free response. So a lot of teachers will go way beyond this, but this is the essential parts for the AP exam. So if you look at the course description, you can see for 3.8, there's a couple things in here worth highlighting. And I've just kind of underlined in red. You can kind of see that there's this red stuff here about relative concentrations. So the problem will usually tell you something is dilute and something else is excess. And that's going to tell you the number of formula units that you need to draw. So like the number of molecules for those ionic compounds. Um, so you should know which one has more in the drawn out picture basically. And then there's this other part here where you need to draw in interactions. So you're going to be drawing like intermolecular forces. Now, a lot of times this is just like placing water around the charged particles correctly. So water has like a negatively charged side and a positively charged side. The electrons are spending more time around the oxygen than the hydrogen. And so if you have the positive charge, the negative side of water is going to be attracted to that. So there's going to be some sort of intermolecular force or interaction between those. And you can see like the hydrogens, they're positive, so they're attracted to the negative, right? And so this guy right here is kind of attracted to both of them. So that's something that you should be able to draw in, though that I've seen less of in the actual like drawing of the models on the AP test. I could see them totally doing that. They're not going to do like the calculations of the colligative properties, but they may have you draw things boiling. And then you might have to do that with ions, drawing with boiling and ions. That could be definitely something where it's like, well, why is the boiling point of like sugary water higher than not sugary water? And you might have to draw in some of those intermolecular forces to show that and then explain it. So there might be something where it's just conceptual where they could have you do that. And then the 7.8, this is very similar. Basically, if you look here, they want you to draw the relative number of reactants. So it's again, this number of molecules needs to be represented in the drawing. And so there's the number of moles, which can be related to the ratio of molecules. So you're drawing out these little molecules, that's going to be related to the moles. And moles might be given from like concentration and volume, because if you have concentration, which is molarity, and you have volume, then you can say how many moles you have then. So it's very likely that you'll have like different numbers of moles of two different things being mixed, and you need to figure out, well, which one's more, which one's less, and how much more or less there is. They usually do it pretty simple for the drawn calculations. Like the math on those problems is pretty simple compared to the math in other equilibrium problems. Now we are going to go through a couple problems here. There is two of them where it's going over representing just molecules of gas, but it's really important to compare that to what we're doing with the ions. So we're going to go through those two problems fairly quickly. And then we're going to focus a fair amount on this question and this question. So we will get to those. But I want you to think about the spectator ions here and how that's related to like a reactant that doesn't react because it's still present. And that's going to be relevant for the problem. So you could think about like HBr breaking down into H2 and Br2. So this is like, I think it's hydrobromic acid. We could say that this is a gas and it is breaking down and forming H2 and Br2. And so you might want to look at this and think, well, okay, there's two of these forming like one of these and one of these. Um, and that is like like the reaction is done correctly and you've got the correct number of reactants and products for that reaction. So this is a reaction, sometimes abbreviated as RXN. But then we want to draw out a model of this showing that the reaction has stopped. And so you could have some sort of initial situation and some sort of final, where we've got final, we've got initial, and initially we had, let's say maybe H is that, and then we fill it in, and BR is filled in like that. So maybe we've got something like this, where they react completely and there's nothing like in excess or anything like that, and we just get like something that's really nice and neat. But it is possible that you had a little bit of extra HBr that wasn't fully able to react. So there may be some kind of like a spectator that's present in the initial and the final, even though there's been this reaction. So there's some reaction that's happened here, and we've taken like the two HBRs and we've turned them into an H2 and a Br2. And so it's like, okay, well, that's been the change, right? So there's some sort of change here. And so we're like subtracting two of these guys and we're adding in one of these and one of these, right? So that's the main idea on this. Not too bad. I don't think that that's too bad. And then if we look at this next one, it is very, very similar. So like we saw in that last problem, we have a problem here where we've got the H2 and Br being represented and reacting. And you can kind of see right here that this is our initial and that this is kind of like our final right here. So we got like our initial and final, and then there's some sort of change that's like moving things over time. And so we can see that this is starting out with what I would do for this is more in line with what I would do for the other problems, is that I write out how many I have of these different ions. And yeah, you can draw them out, but you can also kind of just list them out. So I'm seeing like a number of H2s and BRs. Twos. Oh, this is actually the opposite reaction. So these are now reacting and they're forming some HBr. So there's a little bit of HBr in the final, and we have a little bit of, it looks like H2 and Br2 as well. So it looks like initially we had, was this 1, 2, 3, 4 of these, and then 1, 2, 3, 4 of these. And then it looks like we have only one and only one left over. And we formed 1, 2, 3, 4, 5, 6 of these, I believe. Yeah. So what we could say is that the change that's happened here now is that we had it looks like 3 of the HBRs reacted, right, and then we were able to get, or sorry, 3 of the H2 plus 3 of the Br2 reacted to give us 6 of the HBRs. So like the reaction, if you were to just do it as its balanced reaction, that's a little bit different than what we're drawing out in these pictures. And people get kind of mixed up because they want to draw out like the reaction, just reactants and products in the final situation, but that's not really the case in these problems. The final is kind of like equilibrium, or in the case of the ions, there's like some precipitant that's present, but not everything's formed precipitant because some things ran out. So if we have these guys, the regular balanced reaction, you could just imagine is that, right? But you can see that like you've had three sets of that, um, three sets of those reactions going from the initial to the final. That's the main idea. And then we're going to take that same sort of thinking and try and apply it to this problem, number 13. So if you look at number 13 here, I do unfortunately have some student work on here. I got this problem from a student, but I think that that's okay. We can still go through it, and it's kind of good knowing what the right answer is as well while we go through this, because I think that'll help you kind of understand what we're saying as we're saying it. So C is the correct model, but the question is, why does that work given this reaction? So just take a minute, read through the problem, try and understand it, and then continue with the video, right? So the first thing that I notice when I'm reading this is it's like, which one is an excess? It looks like we've got excess NaCl and dilute AgNO3, and they're telling us which ones are even precipitating out and which ones are still spectators. So it looks like Ag and Cl, those are going to be actually reacting, and so our spectators are going to be the NO3 minus and what is that? The Na, because those stay as ions. They're not included in the net ionic equation, which they've included above there. So we know those are the net ionic, or we know those are spectators. So basically, change is 0 from I to F, going from that initial to final. Like they should have the same amount of stuff in the final and initial situations, or our drawings or lists. So we've got some sort of reaction. We know those spectator ions are involved. Now it's kind of like, okay, well, let's imagine how many Ag and Cls and whatnot we had initially, how many kind of reacted, and how many do we have in this final situation, and what seems reasonable. Because some of these situations are going to have like too much of a certain ion. It doesn't really make sense. So if we look at this problem, the first thing that I notice is that there's dilute AgNO3. So there's like, we could say that this is some Ag plus and a lot of, I think it's the Cl minus. I need to give myself a little more space here as well, it looks like. So we've got some Ag plus and a lot of Cl minus, due to the fact that we've got a lot of that Cl minus there. And so I'm just kind of looking at this and I'm thinking, well, like we're probably not going to have any Ag left over. No Ag plus, because it's all reacted. And the reason it's all reacted is because that was the it was dilute and it's been used up completely by the Ag plus. So the final should have 0 Ag plus, and that's just going to immediately disqualify. Like I think I see that like there's a Ag plus right there, so B gets disqualified. And D also has an Ag plus, so D gets disqualified. So I know those two can't work anymore. And then the question is like, okay, well, if I have excess, then I should have more of the Na than the NO3. So a lot of Na plus and some of the NO3. So there was some NO3. These guys don't react. I suppose we could do that in a different color. We could say that these don't react, these spectator ions, right? So they're not reacting. And so we've got the same number. And so the question is, which one of these has a number that seems reasonable, like A or C? And it looks like with A, there's 1, 2, 3, 4 NO3s and 1, 2, 3, 4 NAs. That doesn't make sense because 4 and 4, like they should have different numbers because one of these was an excess. Like there was excess. Hold on, give me a second. Yeah, sorry. I was just had to think about it for a minute. Yeah, if there's 4 of these and 4 of these, like if you said there was 4 NO3 and 4 Na plus, then there would have been 4 of them here. And that really is kind of odd because what you're basically saying is that because these are in a 1-to-1 ratio from their formulas, like the Ag to NO3 is at a 1-to-1 ratio. So like that would mean that there's 4 Ags and that there's also 4 of the Cl minuses, which doesn't really make sense because these things shouldn't be equimolar. There should be one of them which is in excess to the other. So A, because they're equal amounts of molecules, that doesn't work. That immediately gets disqualified. So what we could say is then instead of 4 and 4, what if we said we've got, I think that's 2 NO3s, and then 1, 2, 3, 4 NAs, and then what was that, 2 Cls? And so what that means was that we had 2 of the NO3s originally, and we had 4 NAs originally because they don't react. And it looks like we had, because remember these should be equal amounts, it looks like we had 2 Ag pluses and 4 Cls, and then they react at a ratio of 1-to-1. So it looks like there was 2 Ag pluses reacting with 2 Cl minuses to form 2 AgCls. But those aren't represented as ions because that's a solid, so it's being represented as that thing in the bottom here. So yeah, C is the correct answer there, and it's very, very similar to what we were talking about in the last problem, where there's something that doesn't change initially and finally, and that kind of helps you understand the other parts of the problem, right? Also, typically these problems, they don't have you drawing in the intermolecular forces, but they definitely could. So just keep that in mind, is that they could have you doing something like little Mickey Mouses to show that how these things are interacting. I think actually, because that should be the negative, that should be maybe attracted to a positive charge like that. So that's something that they may include, but I haven't seen it in typical exams. It's much more of like, what are the number of ions here that should be in solution, given that one is excess and the other one is dilute. And that's kind of how I think about it. So this example is directly from the 2019 exam, and a lot of the recent ones tend to have problems that look like this, where there's some sort of precipitation reaction, like there's this precipitant happening right there, and there's some ions that are involved, there's some spectator ions, and as well as the ions that are actually reacting. Also, what's really important is knowing which one of these is in excess. And I can just look at these knowing that we're having the excess calcium nitrate. So there's excess calcium. So there's probably going to be some calcium ions in the solution. I'm just thinking there's going to be some calcium 2 plus, but the exact number of those I can't like figure out just by looking at this. I have to actually do a little bit of thinking like about the final and the initial and the reaction and these number of spectator ions. So this is very similar to those other problems that we just did. We got to think about what's going on in the initial. We got to think about what's going on in the final. And we got to think about how this change has happened due to the reaction. So I immediately, because this isn't like the ABCD, I can just look at the number of ions here and just figure out those number of ions. And I also know the spectators. So we might as well label those. So the spectator ions is the Na plus and NO3 minus. you can kind of see that those are still aqueous up here. So these are going to stay the same. Like there's no real change between them. So the amount of sodium in this picture, which is like after they've reacted, that's the final. That should be the same for the spectral ions initially, which will help us figure out how much calcium and carbonate we have. So if we look at this final situation, it looks like we've got, what is that, 4 NO3s. So we've got 4 of the NO3s, 1, 2, 3, 4, 2 of the Na pluses, and those should be the same in the initial situation because they didn't react, right? So we've got 4 NO3 minus and 2 sodium plus. And a lot of people, this is where they really get stuck, is that they want this picture to be like the coefficients in the reaction. But those coefficients are the change from the initial to final, knowing that one of these is in excess, right? So if we're looking at these 2 sodiums, it looks like you need 2 sodiums plus 1 carbonate to react, or to be like equally, like have the positive and negative charges cancel out. You know, it's like that formula unit, the Na2CO3. So because there's 2 of these for every 1, you could say that there's 2 nitrates for every 1 CO3 minus. So that's like how much was initially present. So there was like a 2-to-1 mole ratio between the sodium, the carbonate. So there has to be 1 because there was 2 of these guys here. And very similarly, so I'm just gonna make that purple and make this purple so you can kind of see that. And very similarly with the blue, we've got like 4 nitrates, and we knew that there was 2 nitrates for every calcium, and so there must be like 2 calciums here. And so we're able to kind of think about, okay, well, I had 2 calciums. I had 1 carbonate. They should be reacting at a 1-to-1 ratio. So there's like a calcium 2 plus and a carbonate. Looks like that's a 2 minus. Yep, that should be a 2 there. So if these guys react at a 1-to-1 ratio, you get 1 calcium carbonate. So there's a 1 of these and 1 of these reacting to form 1 of those. And so we have 0 carbonates, but we have, it looks like 1 calcium still left over. So we should have 1 calcium drawn in here. It's a +2 charge, and that should work for this drawn model. We only needed 1 of them, and you can think about this like, okay, well, if I had 1, but there were like 2 ones reacted, right? And I had 1 carbonate, 1 reacted, so I've got no carbonates, and we've drawn in no carbonates, which kind of makes sense. All the carbonate, because that's the dilute thing that's reacting, all that's going to get used up. And the one that's concentrated or that there's excess amounts of that stuff, that will usually have some left over of that one. The spectral ions are always going to be left over because they don't react. So that's the main idea with these types of problems. There's one more that I wanted to show you that was on a more recent AP exam. It's kind of related. So I also wanted to go over this problem. This is from the 2021 free response, so it's very recent, very likely to come up again. And it's a really good question for getting at this modeling of solutions. So the first couple of questions are conceptual. I'm just going to kind of discuss them. It looks like we've got 2 different ionic compounds, calcium sulfate, and it looks like lead sulfate. These 2 guys, these 2 chemicals, they're going to be, as a solid, they're going to be in an ionic structure. So there's going to be like plus and minus charges, but they are in a repeating pattern next to each other. So those charges are kind of locked down in place. And so they're not able to freely flow past each other. Electricity requires flow of electrons. So I would say charges locked in place due to, this is going to be the intermolecular forces between these ions. due to forces between them. Yeah, I would just do forces instead of doing IMFs because that's between two different molecules and intramolecular within the molecule. And this is kind of a gray area. Like, is this a molecule? This whole chunk of solid is kind of debatable versus like the little pieces. Because, like, why would you put that plus with that minus and not with the other minus, basically? So they're kind of locked in place there. You don't really need to draw anything in there, but that's kind of how I would think about it. And then we've got these two things that are being dissolved in water. And then we're looking at the electrical conductivity. And it looks like calcium sulfate is higher than that of the PB. And so if it's conducting more electricity, that means there's more ions in solution. So more electrical conduction equals more ions in solution. To move as current is applied. That's what I would say, something kind of like that. And then this is the key part when you're actually drawing in the model. So if we're looking at this model here, they're going to look very similar in terms of this part, having there be some sort of solid, you know, but there's going to be a different number of ions in solution. So the lower conductivity is going to have less ions in solution. So instead of doing 1, 2, 3, 4, 5, 6, I might just do like 3. And then it might be like a plus, a minus, and a minus. And you can, obviously these should be repeating patterns with plus, minus, plus, minus, plus, minus to show that the ions are interacting with opposite charges next to each other. And you could even, just to show that less of it is dissolved, you could have maybe a little bit more of the solid represented here. Something kind of like that. To show you that less of it has dissolved and less of it is actually in solution. More of it is the precipitant or that solid that's insoluble in the bottom. Okay, and then I think that's basically it. And then there's this last piece here adding a little bit of, okay, so there's adding in this sulfuric acid. So they've basically added in some more of this ion. So there's more of these minus ions in solution. And when you put more of those ions in solution, that's actually going to form more of the precipitant because now there's like too many ions in solution. So to take some of those ions out of solution, you need to make more solid. Too many SO4 minus ions in solution. That should be 2 words there. So there's too many of these things in the solution. So more reactant slash solid is formed. And that's what I'd say for that one. All right. I really think this is a good one. It doesn't have you showing the water, how it's interacting with these ions, but it does have you representing different solubilities in a model and having you think about what's going on conceptually. So I think that this is a very good question and very likely to come up because it's not only asking about solutions, but it's asking about equilibrium at the same time. So this is like 3.8 and 7.8 put together in one question. And the College Board, they love doing that because if they can assess more in one question, that allows them to cover more content, right? So be careful with that. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page, and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.